Hello, and welcome to the I Heart Pluto Festival. I am Dr. Jennifer Hanley, a planetary scientist studying liquids across the solar system at Lowell Observatory. This year, we celebrate the 4th annual I Heart Pluto Festival, centered each year around February 18th, the date that Lowell Observatory's Clyde Tombaugh discovered Pluto in 1930. The festival is a community-wide event that includes science talks, family activities, a keynote program called Night of Discovery, which took place on the 18th and featured NASA astronaut Nicole Stott, a Pluto pub crawl, Pluto-themed food and drinks around Flagstaff, and more. We'd like to thank the following sponsors for supporting the festival: Unisource, North Country Healthcare, APS, Arizona Central Credit Union, Dark Sky Brewing, Creative Flagstaff, and the City BBB funds. And a special thank you to Unisource for sponsoring this virtual program. Our program tonight is entitled The Future of New Horizons, an interview with Alan Stern. Dr. Alan Stern is a planetary scientist, space program executive, aerospace consultant, and author. Alan leads NASA's $880 million New Horizons mission that successfully explored the Pluto system and is now exploring the Kuiper Belt, the farthest exploration in the history of humankind. In 2020, NASA selected Alan to fly as the first NASA-funded commercial space crew member aboard a Virgin Galactic suborbital space mission. He will perform astronomical and space physiology experiments. In both 2007 and 2016, Alan was named to the Time 100 list. In 2007 and 2008, he served as NASA's chief of all space and earth science programs, directing a $4.4 billion organization with 93 separate flight missions and a program of over 3,000 research grants. Interviewing Alan will be Melissa Sevigny. Melissa is the science and technology reporter for KNAU, an Arizona public radio station based in Flagstaff, Arizona. She has worked as a science communicator in the fields of planetary science, Western water policy, and sustainable agriculture. Melissa worked for NASA's Phoenix Mars Scout mission during its ground operations on Mars in 2008. She earned a BS in Environmental Science and Policy from the University of Arizona and an MFA in Creative Writing and Environment from Iowa State University. She is the author of 3 books, including Brave the Wild River, which will be published in May 2023. During this program, viewers are welcome to send in questions via the YouTube chat, and they will be answered as time permits. With that, I will turn it over to Melissa and Alan.
All right, welcome everyone. I'm really excited to be here with Dr. Alan Stern. I wanted to start by asking, well, it's been 8 years, believe it or not, since New Horizons flew by Pluto. Where is the spacecraft now and what is it up to?
Well, first let me say thank you to Jennifer for the great kickoff for today. And Melissa, it's great to be working with you again. So New Horizons is on an escape trajectory from the solar system. It's traveling so fast that it's flying above the escape speed of the sun. And so it's actually on its way to interstellar space. But it's not there. The Voyagers have gotten that far, but they launched, in the 1970s. New Horizons launched in 2006. And is traveling at a speed of about 3 astronomical units per year. A little bit faster than that, actually, and very similar to the speed of the Voyagers. But the spacecraft is now just about 56 times as far from the sun, 56 astronomical units away. It's 56 times as far away as the Earth is from the sun. To put that in perspective, the Voyagers are more than twice that far, because they had such a head start. But also to put that in perspective, we're now getting close to twice the distance we were at when we flew by Pluto. So we're very far away.
That's incredible. And it's hibernating right now, is that right?
The spacecraft is hibernating for another couple of weeks. We do that to save money and also to save wear and tear on the avionics. And on March 1st, the spacecraft will emerge from 9 months of hibernation and will be active for at least the next 2 years. Even in hibernation, 4 of the scientific instruments are collecting data and putting those on the recorder. So we're doing science even when we're hibernating. But once we come out of hibernation, we can also downlink that data, and we can do much more complicated operations like flybys or looking at Kuiper Belt objects that we pass in the distance, doing other kinds of science.
Okay, cool. So just around the corner, it's gonna wake up again. That's exciting. Tell me about this kind of outer region of space that it's exploring. What's out there?
Well, that's a good question. We actually don't know. The solar system, is pretty well known in the inner reaches, but as we go farther and farther out, it becomes more and more terra incognita. And that's because everything that we spot from the Earth relies upon our detecting reflected light from those objects. And many of the people listening will remember from science class that as you go farther and farther from a light source like the sun or a lamp, the brightness drops down with the square of the distance because the light has to fill a shell. And the farther out the shell, which has a surface area that's 4 pi r squared, where r is the distance, it keeps dropping. All that same light has to get diluted more and more further out. So when you get out in the Kuiper Belt, things are much fainter. They're very softly lit. Where we are, things are literally thousands of times more faintly lit than here on Earth. But to make that even harder, all that light that's reflected, no matter how feeble, has to come all the way back. And that's another r squared. So in effect, it's r squared times r squared, which makes things get fainter as you go farther and farther out, like the fourth power, r to the fourth, the distance to the fourth power. So all that's to say that it's very hard to spot things that are this far out. Even with the largest ground-based telescopes, it's right at our capability limit. And what we know is we're in the outermost reaches of the Kuiper Belt. We don't really understand. We don't have a good map of the outer Kuiper Belt. We know that there are Kuiper Belt objects out there and that we'll keep passing Kuiper Belt objects at least until 2027, maybe even a few years past that as we travel farther and farther outward. The other thing that's out there is the sun's atmosphere, the so-called solar wind, which professional solar scientists call the heliosphere. And we're in the outer region of the heliosphere too, and we will eventually, in the 2030s, pass beyond the heliosphere out into interstellar space with New Horizons. So what we see and what we observe is this distant reaches of the heliosphere, first explored by Voyager, but we have much more sophisticated instrumentation and a variety of instruments that Voyager didn't carry. So we're making a new generation of exploration of the heliosphere. And we're studying Kuiper Belt objects that we pass at greater and greater distances, looking for a third flyby target after Pluto and the KBO aircraft, and doing other kinds of science that you can only do when you're very far from the sun, that no other spacecraft can do, that no ground-based observatory, even the James Webb and the Hubble can't do this stuff because they're not far out.
Okay. Tell me a little bit more about the Kuiper Belt. As you said, New Horizon got the first ever close-up look of 2 Kuiper Belt objects. Why is that significant? Why is it important to study this region of space?
Right. Well, I would first I would like to clarify that if by 2 Kuiper Belt objects you mean Pluto and Arrokoth, we would really consider Pluto a dwarf planet, and the small objects like Arrokoth to be the KBOs, the Kuiper Belt objects. Because if everything in the Kuiper Belt is a Kuiper Belt object, the term becomes a little meaningless. In fact, by that definition, New Horizons is a Kuiper Belt object. It's an object in the Kuiper Belt. So we don't want that term to become meaningless. But the Kuiper Belt is a really interesting place. It's very far from the sun, so the temperatures are very cold. And that means that chemically, things are very well preserved over time. And we know that there are some objects, like Arrokoth is one example, that were formed very far out there in the Kuiper Belt. So they're a sample of the very distant solar nebula and the way that planet formation got started out there by forming much smaller objects we call planetesimals, the building blocks of planets. And then there are much larger objects the size of continents, like Pluto. And there are also populations in the Kuiper Belt that weren't born there. They were gravitationally transported out there during the formation and rearrangement of the giant planet region of our solar system. So we have samples from the middle solar system that were moved out into the deep freeze where they were very well preserved. We have objects that were born out there and were always cold and are also well preserved. And then we have objects, these small planets that are out there as well. And so it's a really interesting region for understanding, A, the origin of our solar system, B, the nature of dwarf planets, of which there are a lot out there, and finally, the whole building block process that led from dust grains to boulders to planetesimals the size of counties to dwarf planets the size of continents. And so that's really why this mission came to be, because back in the early 2000s, the very first planetary decadal survey ranked the exploration of the Kuiper Belt as the #1 priority, because we knew so little about it and it promised to teach us so much. So as a result, NASA got funded to do the mission that became New Horizons.
All right, that's awesome. I want to bring in a question from the audience. How does New Horizons maintain power? Does it have solar panels or does it have a limited power source? And if it does have solar panels, how effective are they being that far from the sun?
So that's not a question, that's 4 questions. Let's see if I can remember them all. But the basic answer is whenever we send spacecraft that far from the sunlight is too weak and the temperatures are too cold to use solar arrays. So ever since the first missions that went very far out, we have to use nuclear power. And New Horizons, just like the Voyagers, and like spacecraft like Cassini that a lot of people here know about that orbited Saturn, like quite a number of spacecraft, we have a nuclear battery on board. It's called an RTG, and that stands for radioisotope thermoelectric generator. But it's just a fancy word for nuclear battery. In fact, I like to say, I call RTG the really terrific generator because it's the only way to work that far from the sun. It's fueled by plutonium, which is a radioactive element, which generates a lot of heat from its radioactive decay. And we turn that heat into DC electricity to run the systems and the experiments on board New Horizons. But like every radioactive element, it has a half-life. And that means that every year, there's a little less heat produced as the plutonium starts to dim, to die out. When we launched, the plutonium on board was capable of generating just about 250 watts to run everything, basically 4 light bulbs. But every year, 3 watts less. And now we've been in space for 17 years since launch in 2006. And the spacecraft now generates just a little under 180 watts, so 3 light bulbs. So we're running on a constrained power budget. That's the bad news, is we have to be more careful with power management. The good news is we have enough power in that battery to run that spacecraft for another 25, maybe a little more, maybe out to about 2050. At some point, the plutonium just won't produce enough juice to run the computer, one experiment, and the transmitter, and we'll have to quit. But until then, unless something breaks, and so far, nothing's broken, we got plenty of fuel and plenty of power to run it for another 25, 27 years.
Wow, that's incredible. So you still have a lot of time to do science. What is the next thing that New Horizons is going to look at?
Well, immediately, we're studying the heliosphere as we speak with 4 different scientific instruments, and we're trying to develop a technique to use our 5th scientific instrument to study. We study the gas, we study the radiation, we study the charged particles, and we study the dust, all as a function of distance as we move further outward. In terms of Kuiper Belt objects, the next Kuiper Belt objects that we'll observe will not be a close flyby, but an object that we study from a distance this coming fall in October. And we'll also in October be looking backwards towards the sun. This is really cool. We're going to be looking at the planets Uranus and Neptune, which of course Voyager flew by both. And they've both now, that was decades ago. So they have moved around their orbits, and they're in this, the planets are in different seasons than they were at the time of Voyager. And we can look back at these objects and study their the way they reflect sunlight at what are called high phase angles that you can't do unless you're very far beyond them. And we're the only spacecraft beyond them with the capability of looking at them. And when you study their photometric properties at high phase angle and combine that with data from the Voyager flybys and even from ground-based telescopes or the Hubble or James Webb, you can learn about the energy balance inside the planet. And that then relates to how they produce meteorology and other things. So we're going to be making some contributions that no other spacecraft can make by looking at Uranus and Neptune at these high phase angles in the fall and again next year to compare to ground-based measurements and put together a picture of their energy balance that you could not do if you only had telescopes down here in the inner solar system. So we're pressing New Horizons into service for a whole variety of different purposes, things that you can only do by being in the Kuiper Belt or farther out.
Right. Yeah, that's really neat. You've mentioned the heliosphere a couple of times. Can you kind of describe it? I've always pictured it kind of like a bubble of the sun's influence, but I'm sure you can describe it better than that.
Oh, Melissa, that's a really good explanation. It's a bubble. And the reason it's finite is that out there in the galaxy, there's a gas, which is called the interstellar medium, the stuff between the stars. And as the solar wind moves outward from the sun, it rarefies because it's got to be diluted as it moves further and further out and cover more and more area. Same way that light declines, like I talked about, like the square of the distance. So the solar wind gets more and more rarefied. And so the pressures go down, and eventually it reaches a pressure balance against the interstellar medium, a little more than 100 times as far away from the sun as the Earth is. That's where New Horizons is headed. So currently we're within the cocoon or the bubble of the heliosphere. Once we get somewhat further out in the 2030s, we'll pass out of the heliosphere and into the interstellar medium across that pressure balance.
Cool. Okay. And you have instruments that the Voyagers don't have to actually kind of study them.
We have particle spectrometers that study a critical energy range for the dominant population of particles out there that creates this pressure balance. They're called pickup ions. We also have the ability to map the neutral gas, that is the uncharged hydrogen, all through the heliosphere, and even to tomograph it as we go outward. So we can see its 3D structure. And we have a dust detector on board that records dust impacts as a function of their distance from the sun and how big a particle is striking the spacecraft. And that's a capability Voyager didn't have. So we can perform a variety of different studies of the neutral gas, the charged particles, and the dust to get a more complete picture of the heliosphere by a long shot than Voyager could. Now, that's not to say they didn't do good stuff. They did pioneering work. And they had one instrument that to study the heliosphere that we don't, called the magnetometer. So they had their strengths and we have our strengths, but our instrumentation was built 30 years later. It's much more sophisticated. It's built in this century, not, in the dark ages of 1970s electronics.
Sure. Okay, cool. A reminder to the audience, feel free to send in your questions via the chat. We'd love to hear from you. Ellen, what for you has been, this New Horizons has been plugging along for, I think, 17 years in space now. What has been the most surprising thing so far?
Well, so I think scientifically, probably, there are many answers to that. To be fair, the completely different discoveries at Pluto than at Arrokoth, for example. But I think the biggest ticket was the discovery of just how active and how complicated planet Pluto is so far from the sun in this very cold region where there's no obvious source of energy to power all that geologic activity and meteorological atmospheric activity that we see. And for a long time, as we were flying across the solar system, there was a scientific debate about whether Pluto would be geologically deader than a doornail, kind of like the moon, or whether it would be super active, but no one could imagine how it could be active. And it turned out that Pluto's super active, even today, that the geology and the meteorology are both changing the planet in ways that are reminiscent of the way that Mars and the Earth are active. And that's rewritten the textbooks. And I think that's probably the biggest headline. But other people might tell you that there are other important headlines, like the discovery of how planetesimals form with the flyby of Arrokoth. That's huge. And many other discoveries at Pluto as well.
And Arrokoth, for those of you who remember, that it's kind of the snowman shaped. It's got, rocks glomming onto each other. Can you tell us a little bit more about what that showed you, about how things form in space?
Yeah, I didn't bring any pictures, so we got to do this either from people's memory or by doing things like this, right? But all of the pictures there, and by the way, this is the first pristine, undisturbed planetesimal ever seen. So it's really telling us for the first time what they're like. And what we found is that there are a whole variety of clues when you look at the geology of the object that show us that it formed through a process of very gentle accretion that points to a particular theory among the sea of theories that were out there about how planetesimals form in little local collapse clouds. And there's really no way around that Arrokoth must have formed that way. And the other theories that involve more violent collisions with objects coming from much farther away, not local, just don't work to produce what the object that we saw. So if the object we flew by was typical, and we just pulled a random one out of the bag, so it should be typical, that's telling us that all the planetesimals, all the starter objects that eventually built up to make small planets like Pluto, formed in this gentle accretion way. And that has really simplified thinking, because we used to have multiple competing theories and didn't know which one. And now we know this one branch of physics is how it really worked.
Okay, neat. We've got some questions coming in from the audience. With the Deep Space Network DSS-43 Canberra going offline for maintenance, is that going to impact communications to New Horizons?
Yeah, well, DSS-43 is one particular antenna at the Canberra station. It's the biggest antenna there and the one that we use. And Canberra is the most important of the Deep Space Network sites for us and for Voyager, because all three of those spacecraft, both Voyagers and New Horizons, happen to be flying into the southerly declinations of the southerly sky. And so we get better communications from the station down in Australia than we get from those in the Northern Hemisphere for that reason. Same for Voyager. And so when they go offline for some months to do upgrades and repairs, we do suffer, but we can still use the other two stations and communicate, and we will. And by the way, Canberra went down for, I think, 13 months during our first extended mission. That's one reason that we're still sending Arrokoth data home, is we didn't get to use Canberra for those 13 months. But it doesn't stop us from communicating. And we have very large, by spacecraft standards, large solid state memories on board, flash drives, basically. So we can buffer data as we take it. We don't ever lose anything. Even if we can't send it all home that week or that month, we can keep it on board the spacecraft for years until Canberra comes back online and we have more communications capability, and then start sending it to the ground.
Okay. There's a related question about communication. How much power is used for communication with Earth, and how accurate must the transmitter be aimed?
Right. Well, we have a antenna that's about 3 meters across. And that antenna is what focuses the beam. And at our particular transmission wavelength, which is 4 centimeters, it's in the X band, the beam is about 1/10 of a degree across. So we have to point to the Earth to within 1/10 of a degree in order to communicate at high data rates. And we don't have a very high-powered transmitter. It's 30 watts of transmission power, not 30 kilowatts like a radio station, 30 watts. And so even with these giant antennas like at Canberra and the other 2 deep space network stations that are the size of football stadiums, the end result is that we can communicate at about 1,000 bits per second from where we are, which is pretty slow. You wouldn't stand for that reading your email, but it does work. We can transmit many gigabits per year by using a lot of transmission time. That's what we do. But with a spacecraft that only has 180 watts, it's a good thing the transmitter's only 30 watts, or we wouldn't have power for anything else.
Okay, and another question from the audience, kind of in the same vein. What were some of the engineering hurdles you had to overcome given the small amount of power you have?
Well, we had to design a very low power spacecraft. And so we had to get parts that didn't consume very much power. We had to design a concept of operations like that. It complicated some of the fault protection software. For example, you can't keep your backup systems online. You don't have enough power. So you have to be able to detect a fault and boot something up, turn off the system that's misbehaving and boot up its sister system to come online without tripping the power limits. And so that's a little bit of a juggling act. But fortunately, the engineers know how to do all of that. And that was not our greatest problem at all. We had bigger problems with just building it in a hurry to make the launch window because we needed to fly by Jupiter. And that was only available in the year 2006 for us. And doing it on much lower cost than Voyager, which required a lot of breakthroughs in how we designed the mission and then went about building it. The tech was actually mostly proven by the Pioneers and the Voyagers. We just used more modern day versions of that.
Okay. The flyby of Jupiter you mentioned, that was required to kind of slingshot the spacecraft, right?
That's right. That added speed. And had we not had that flyby of Jupiter for a launch in 2006, we would have taken 14 years instead of 9.5 to get to Pluto. And worse, without Jupiter, we couldn't have launched after 2007 at all for 10 years until Jupiter came back around its orbit. So in order to get on our way, we really needed to make that Jupiter launch window.
Right. Okay. Kind of going back to our conversation about Pluto, you mentioned that there are a lot of dwarf planets out there. How many is a lot? And do you think, is there any way of knowing if any of them are as active and interesting as Pluto is?
Right. Those are great questions. In the Kuiper Belt, we know of about a dozen dwarf planets. They've all been spotted by telescope. Pluto is one. Its big satellite, Charon, is another, but there are objects like Eris and Quaoar and Ixion, and could name 7 or 8 more, that orbit all across the Kuiper Belt. We have evidence that 1 or 2 of them may be active, but frankly, if we could send spacecraft to all of them, we might find out they're all active. We just don't know. The only 2 that we know about in detail are Pluto and Charon. Charon seems to be mostly inactive because it doesn't have any volatile materials on its surface. Pluto is hyperactive. So they're kind of a weird pair that spend all this time together in the same place, same radiation and collisional environment, but have really diverged in terms of their geological activity very, very much over time. Probably the difference being Pluto is larger and able to generate that internal activity, and Charon is smaller and can't anymore. But we have some evidence that objects like Eris are active, maybe as active as Pluto. But it's very circumstantial and very tentative evidence. not the kind of evidence we have for Pluto where we've seen it up close. We really need more missions to the Kuiper Belt, particularly to the dwarf planets of the Kuiper Belt. And I think that'll come, so that'll be exciting.
That's good. Yeah, that's good to hear. We got a follow up to the slingshot question. Does New Horizons have a propulsion system, or is it mostly powered by those slingshots?
So the answer is both. We do have a propulsion system on board, and it's used for two purposes. One, I'll use my cell phone as the spacecraft model, is to point the spacecraft, we have to fire jets. And then we have to fire other jets to stop, to point the telescopes in any given direction for a flyby, to track targets or things that we pass in the distance, or to look back at Uranus and Neptune, or to point our antennas at the Earth. We also can use the same thrusters, not just to turn the spacecraft, but to propel it or even slow it down a little, but only to a very limited degree. We have a tiny fuel tank on board. Most of the speed of New Horizons is due to the rocket that launched us, which was the size of a downtown skyscraper called an Atlas V. And then we boosted that with the Jupiter flyby. And the propulsion on board the spacecraft really can't change our speed very much. It's mostly for just homing maneuvers as we get close to flyby targets, to do the very fine mid-course corrections to make sure that we end up on time and on target to the accuracy that we need. So our speed is basically fixed by our original launch in the Jupiter flyby, and the spacecraft then uses propulsion for fine control and for pointing.
Okay, cool. Thank you. Another question from the audience. Looking ahead, what are the future prospects for the New Horizons mission, and how might it contribute to our understanding of the Kuiper Belt and beyond?
Well, as I said earlier, the spacecraft's very healthy. Nothing's broken. We're not using the backup systems because anything's broken. Sometimes we do use them either to test them or just to take the load off the primary systems for a while, to give them a break. And the spacecraft has fuel and power to run 25 or more years. And we'll be in the Kuiper Belt for at least 5 more years. And then beyond that. But so we're using the spacecraft to study Kuiper Belt objects that we pass in the distance. We've now studied, I believe, 32 of those, along with some of the dwarf planets we studied in the distance. And we're looking for a next flyby target. That's very challenging because things are so faint, as I described earlier, very far out there. It's kind of a needle in a haystack problem. And what makes it even harder, particularly for those who are listening, who are amateur astronomers, they'll appreciate that the direction of our travel is in the direction of the constellation Sagittarius, which means towards the center of the Milky Way galaxy. Those are the densest star fields there are, which means that we're looking for faint embers against backgrounds that have gazillions of stars. That's not a technical term, but you know what I mean. So there's a lot of what we professionally call confusion due to the fact that these little faint things can be on top of a star at the time we take a picture of it and hidden in the glare of that star, even if that star is super faint, millions of times fainter than your eye can see. So we have to use tricks like advanced machine learning software to help us spot those faint embers. But we're looking for a next flyby target. I don't know if we'll find one. I do know we are the best people in the world using one of the biggest telescopes in the world, the Subaru 8-meter, with the very best camera in the world for wide field searches of the Kuiper Belt. It's called, get this, Hyper Supreme Cam. And so we're looking very hard, but we have to find something that we can get to with the remaining fuel. And to put it in everyday terms, like a car, I'm down to 1/8 of a tank. Now, it only took about 1/8 of a tank to do the aircraft flyby, so it's plausible. And I'd be willing, and I think NASA would approve, using all the remaining fuel to get one more flyby because it's so valuable. But first, we got to have a target that's within that fuel supply, that reach of a mid-course correction to take us there. And we haven't found that yet. Now, it took 4 years to find Arrokoth, and we've just been searching for 3 years in this really dedicated way. We're going to keep searching for at least a couple more. So cross your fingers, cross your toes. The best people in the world are on it. I mean that. The very best Kuiper Belt search team ever assembled works for New Horizons. And they're using, as I said, the best camera on one of the biggest telescopes in the world. So if anybody's going to find it, we're going to find it. And we work at it very hard.
Yeah, that's exciting. Yeah,
yeah.
Very cool. I wanted to kind of step back and ask kind of a bigger picture question. Why do you think that we should do this type of exploration? How does humanity benefit from going out into space and learning new things?
Oh, no pressure there, right? That's a great question, and it's totally legit. I think that there are kind of two answers. One is to develop new scientific knowledge, to learn about our place in space, our solar system, and how it came to be, the origin of it. And in that, what New Horizons has done has been completely pioneering and completely revolutionary. People talk about some missions rewrite the textbook for this or that about Mars, for example, or Jupiter. In our case, we wrote the textbook from scratch because we knew so little to speak of. And it was really the first mission to a whole new region of the solar system. That's one reason we do this. A second reason is a term many of your listeners will be familiar with: soft power projection. Unlike a lot of other countries, the United States has the capability to do these very far away missions, and other nations see that we are explorers and see that we have a capability that really no other nation on Earth has been able to demonstrate in the deep outer solar system. Every kid in every school system, pretty much everywhere, that reads about their lessons in astronomy and the solar system see names like Voyager and New Horizons. And that's basically soft power projection for the United States. It's branding the United States as explorers, the developers of knowledge, people who spend their taxpayers' dollars to do something for all humankind. And then I think the third and final answer I'll give, which we saw demonstrated in spades at the Pluto flyby and the Arrokoth flyby, is how much it excites people to see this kind of exploration. We had, no exaggeration, 2 billion visitors to our website in one 48-hour period around a Pluto flyby. 2 billion is way too many for just my mom clicking over and over again, right? People from all around the Earth, and school kids that get turned on to STEM education because they see, like in our case, the flyby of Pluto was the first time we've been to a new planet since Voyager in the 80s. So for 40% of Americans alive when we did the Pluto flyby in 2015, they'd never seen anything like that. They were either not alive or too young at the time of the last Voyager flyby, which was Neptune, to even remember it or to have been there in any sense. So it was the first 21st century flyby of a brand new planet. And the overwhelming public response to that, has been demonstrated by all those web hits and other things, 500 newspapers the next morning on the front page, on all 7 continents, those kinds of things. And so I think the third reason for doing this kind of exploration is the way that it inspires kids in particular to go into STEM careers, which are hard, math and science. We need those engineers. We need them to power the economy of the 21st century.
Yeah, absolutely. You can't beat the experience of seeing a whole new world revealed. A question from the audience, which I think a lot of people are wondering: will there be another mission to Pluto?
Of course, there will be another mission to Pluto. We just don't know when or who. And I say that with confidence because when I was a kid, and even when you were a kid, it took entire nations just to put something in orbit, and now companies do that. And now individual private companies send missions, not just to orbit, but to the moon and to Venus and to Mars. And in the decades to come, we're going to start seeing that private enterprise do things much farther out in the solar system. So who knows if it'll be some future Elon Musk and whatever they call their corporation that's next to Pluto, or it's the United States with an orbiter mission, or maybe it's the Chinese, maybe it's one of our competitors who'll do that. But Pluto proved itself so scientifically seductive, and New Horizons opened so many questions that we could not answer, like the nature of Pluto's underground water ocean, that I'm sure there'll be another mission to Pluto, if not multiple missions to Pluto in the future. I hope I see it.
Yeah, that was great. And we're coming down to about our final 5 minutes. So for the audience, if you've got any burning questions, now is the time to put them into the chat. Alan, I wanted to kind of wrap up today by asking you about, you have your own opportunity to go to space soon. Will you tell us about it?
Sure. I love talking about that. Yeah. As was mentioned in the introduction, a proposal of mine was selected by NASA to fly on a suborbital mission and I was actually selected to be the first researcher funded by NASA to bring an experiment to space on a suborbital mission. I'll actually be flying 2 different experiments on the same mission, and I hope that that's very soon. Probably next year. I say probably. I should say possibly next year, because I don't really know the schedule yet. They haven't finished their test flights, so we don't have a firm schedule, and NASA hasn't been manifested on a particular flight. But we know that it's at the front of the line, and we know that it's funded. And the experiments are already built and tested, and we're ready to go when they are. So I'm really looking forward to that. Ever since I was a kid, I wanted to fly in space. Who didn't, right? And actually, the way it's working out, I'm going to get to fly at least twice. So I'm raring to go.
Cool. Okay, that's exciting. Yeah. Looks like a final question. We might have time for 1 or 2 more if people still have questions out there. But from the audience, is Pluto drifting away from its orbit?
No, Pluto's on its orbit, and the orbit isn't even drifting away from the sun. It's actually an orbit that's stabilized in a way by the way it interacts with Neptune's gravity. That, coupled with the way that it interacts with the sun's gravity, keeps it pretty well locked in place. So Pluto's been following that orbit for billions of years, and it will continue to.
Okay. And will you tell us a little bit more? We've got just a few minutes left about the experiments you're going to do when you're in space.
Sure, absolutely. So the particular experiment that's the centerpiece is to understand how well the Virgin Galactic spaceship can be used to do astronomy. We've been using suborbital rockets, unmanned rockets, to do suborbital astronomy for a long time, but you can fly on Virgin Galactic for much less money than these so-called sounding rockets, the unmanned rockets. So using these commercial tourist vehicles to do science could be a very cost-efficient way to do things, and could allow us to fly a lot more flights for the same amount of money, to get a lot more data. But first, we have to know how good the vehicle is for doing this. And the critical thing is, how good are the windows that the telescopes have to look through? And it's not that we don't understand what the windows are made of. We do. We understand their reflective coatings, all those things. But when you really fly them in the real world, it's the little details that matter, like the amount of exhaust soot or film that gets on the windows on a given flight. And you can't simulate that. And the amount of glint off the windows from the light scattering off the sphere of the Earth, but also off the wings of the spacecraft. So what I'm going to do is take an experiment called the Southwest Ultraviolet Imaging System, or SWIS, that I was principal investigator for, and which flew on the space shuttle. We take the same gear that's already proven, it's flown in space multiple times, and look through space shuttle windows. And we're going to look through Virgin Galactic windows at the same star fields and see how the data compares, so that we can determine how well the vehicle is suited to doing astronomy compared to, for example, a space shuttle, which did a lot of great astronomy. The other experiment is I'm going to be wearing a biomedical harness to find out how fast my heart is beating and what my blood pressure is all about and all that, as a researcher in space, not a tourist, but someone who's got a job to do and some time pressure and so forth. We hope to eventually get a big database by flying that kind of equipment on dozens or even hundreds of people and really get a statistical sample. I'll be the first. So those are the two experiments. One's passive. I just wear it, turn it on before we launch, wear it throughout the flight. The other one, I actually have to get the gear out and point it out the different windows and get it restowed after we take the data to get the goods.
Wonderful. Thank you so much for everyone who's sending questions. What great questions. We're at the end of our time. Alan, do you want to make any final comment?
Well, I do just for a few moments. First, thank you for a great interview. And thank you, Lowell, for asking me to come every year and speak at this meeting, sometimes in person, sometimes when I'm far away like this. And thanks to Lowell for putting on the iHeart Pluto Festival every year. It really means a lot to a lot of people. And I'm looking forward to being there in person, maybe next year, rather than remote like this. I hope the rest of the conference goes well. Thank you.
Jennifer?
Yeah, so with that, I just wanted to thank both Melissa and Alan for a very fascinating discussion about New Horizons and future work that's going to be done in the Kuiper Belt. And thank you to everyone who was watching and submitted your questions. There were some great questions, and look forward to doing it again, like Alan said. So thank you, everyone. Have a wonderful evening.
Good night.